All right, so in this video, I wanted to go over a really common motion of a charged particle in a magnetic field. And sometimes it's called the cyclotron motion. It's sort of a basic tenet of how charged particles move in magnetic fields based on this more restricted situation, and that is that charged particles tend to circle around magnetic field lines. In fact, sometimes the term is used that they're frozen to the field lines because of this motion around the lines. To sort of get introduced to that idea, it's best to look at the specific situation where the velocity of the charged particle is exactly perpendicular to the magnetic field itself. So over here in this picture, what I'm representing is that there's a magnetic field that's going into the plane of the screen. That's the X's, remember that goes into. And then you can see that I have a positive charged particle moving with a velocity v as shown. Now what happens in this scenario because the velocity vector and the magnetic field vector are perpendicular to each other, that's going to make things a little simpler. And we're going to use the right-hand rule to figure out the direction of the force. I don't want to confuse things because I know it looks like I'm using my left hand when you watch the videos, but if we do V cross B for a motion to the right and magnetic field into the page, we would find a force upward. So this is what the force would look like at that instant in time. Now, because of that fact, as this charged particle is moving, the velocity vector is going to be deflected. And so a little bit later, we might see this charged particle moving more like this. And again, if we look at the force using the right-hand rule, it's going to be like that. And if we continue a little bit more, maybe the charged particle's like this. And the force now is like that. And eventually what we're going to see is that this charged particle is going to trace out a circle because the force that it feels, and you know me, I'm not great with the drawing, but what I wanted to show is those force vectors are going to be constantly towards the center of the circle. And left alone, this charged particle is going to end up settling in to a circular path with a particular radius, and it's going to maintain its speed while, of course, its velocity will change. And we can find a lot of different special quantities that describe the motion that this charged particle is going to be going through. And some of the ones that I wanted to look at how we can find them are listed right here. So the first thing that I want to look at is, let's find the radius. And we're going to use the basic idea, Newton's second law, force equals ma. Now the force that's acting on the charged particle, of course, is the force due to the magnetic field. Because the magnetic field is perpendicular to the velocity, we can write the magnitude of this force as just QVB, because the angle between them is 90 degrees and the sine of 90 is 1. So on this side, we can put QVB. Now, because of the fact that this particle ended up going in a circle, means that it's undergoing a centripetal acceleration. And if you remember from first semester, centripetal acceleration is described as v squared over r. So this is going to be equal to mv squared over r. And so that allows me to get started to find all these quantities. And to be honest, I don't know what any of the expressions are for these quantities, but I know I can always find them if I start here. In fact, I have them all written down on my paper, and I still don't know what they are because I just don't bother remembering them. I'll just figure it out. So that's the great starting point, that the force, which is QVB, is equal to the mass times the acceleration, and the acceleration is centripetal, so that's v squared over r. There we go. Now, if I want to rearrange this to solve for r, I'm going to multiply both sides by r, and on the left-hand side, divide by qvb. And you can see I got a v squared on top and a v on the bottom, so one of those v's is going to disappear, and I'm left with mv over qb. So basically what we find is that the radius of the particle's motion is going to depend on a couple things. It's going to depend on its mass, its velocity, its charge, and the strength of the magnetic field. But in any case, we can use that relationship and find that radius. Now the period is something else that we might want to know. The period is the amount of time it takes to go through one complete revolution. Or once around the circle. So for that, I just use velocity times period is equal to 2 pi r, right? And I just found r, and so if I solve this expression for t, which what I've done is this is simply rate times time equals distance. If I take the speed times one period, the distance it will go is the circumference of the circle, which is 2 pi r. So that's where I got this expression. If I rearrange it, I get t is 2 pi r over v, but I just found my expression for r, which is mv over qb, and then I divided by the v that was on the bottom there. So I'll step away so you can see that. Actually, notice the velocities cancel out, and I got 2 pi m over qb. And so that is what the period depends on. Notice the period ends up not even depending on how fast the particle's going. It only depends on the charge and the mass and the strength of the magnetic field. Finally, sometimes we want to know the frequency of the motion. The frequency, of course, is just the inverse of the period. And so the frequency, which remember what the frequency represents, is the number of complete oscillations or the number of complete circles it will complete in a second. Remember, the units of frequency are numbers per second. So I simply take my expression for period and flip it. And that tells me what the frequency is. Sometimes this is referred to as the cyclotron frequency because that is the motion that is used to contain charged particles in magnetic fields. And that motion is sort of a characteristic of what you're dealing with. And also, again, keeping in mind that this is a very important motion of a charged particle. What would happen that is more interesting is when the particle comes into a uniform magnetic field, if instead of being strictly perpendicular to the field as it was here, if it has an angle to that magnetic field, we can break down the velocity into a component that is parallel to the magnetic field and one that is perpendicular to the field. The parallel component of the velocity, as you know, will not be affected at all by the magnetic field because when you move parallel to the field, there is no force. The component that is perpendicular to the field is going to create that circular motion. So what will happen in the more general case where the velocity is just somewhat angled with respect to the magnetic field is you will have a combination of going around the field in a circle, but also moving along the field because of the parallel component. That ends up creating what we would call a helical path, and that really describes how charged particles move with respect to magnetic fields. That's actually really important when we think of phenomena such as the aurora, because charged particles from space enter into our magnetic field of the Earth and start spiraling down the magnetic field lines until they hit the atmosphere, where those charged particles will excite the gases and cause them to give off light, and that's how we create aurora. So that's just a short little derivation or explanation of the special motion of charged particles in magnetic fields. There are other applications that you'll read about in your book that deal with this type of motion.